Okay, we're looking at the limit of a sequence. And when we look at the limit of the sequence, here's the definition. It's actually a pretty complicated definition, but it says L, let L be a real number. Then the sequence with the terms A of n has a limit L as n approaches infinity if, given any positive number epsilon, we'll talk about that in a second, there is some other positive number m such that any n greater than m, we have this statement is true. So let's break this down just a little bit. What does this statement mean? Well, a of n is the nth term, and L is the limit. And so as n goes to infinity, what should happen between the nth term and the limit? Of course, they should be really close. Okay? They should be really close. And so close, in fact, that if we take a look at a couple different functions, for example, let's look at this function, not a sequence, but a function. The limit as x goes to infinity of 1 over x of the function. So we're riding on this function, we're riding. Of course, this limit we're going to say is equal to 0. Now, the trick to this is that this is a function. So this is not a sequence. And what's the difference between a sequence and a function? Well, of course, a sequence is just a list of these values. But if you look at the same sequence representing, the similar thing for the function, at 1 it's 1, at 2 it's 1/2, at 3 it's 1/3, 1/4, 1/5, 1/6, until eventually, of course, this limit is essentially approaching 0. And so what we say is we write the limit as n goes to infinity of a of n of the terms equals L. And we say that the sequence converges to L. If the sequence does not converge, we say that the sequence diverges. A way to interpret this part right here is this little sentence here. A sequence has a limit L if there is an n value somewhere way down here down the line where every n value bigger has a distance from L smaller than some tiny error. In other words, this absolute value of term minus limit is less than some really small number. And if it's less than that really small number, it means it's really close. We're not going to have to prove them, and it's actually going to seem really simple. It's going to be just like taking a limit of a function, but it's going to be of a sequence or a list of terms instead. One thing to note is any of the limit properties that were allowed in like chapter 2 are still allowed here. So, the limit of two sequences added together is the same as their limits added together separately. And same is true for difference, product, constant multiple, and quotient. So those limit properties also still exist. Let's go ahead and find our first limit. So let's find the limit. Let's determine whether this sequence converges or diverges. Converges has a limit as x goes to infinity. Diverges, no limit. Or the limit goes to infinity. Because if you look again at our definition, the definition says explicitly the sequence has to have an L real number, and infinity is not a number. Okay, so let's take a look. Does this limit, or does this sequence have a limit? And so we're going to do the limit as n approaches infinity of 2n minus 1 over n. Now, some of you obviously right away are going to say it's 2, which is fine. If you want to prove it more strictly with all those rules and in a more basic way, you could always go like this. The limit as n goes to infinity of 2n over n minus 1 over n. And of course, that you can break that up into separate limits using the rules of limits. We do not need to do this, but just as a reminder, of 2n minus the limit as n goes to infinity of 1 over n, which of course is going to equal these n's cancel. So the limit as n goes to infinity of 2 is, of course, 2, minus the lim as n goes to infinity of 1 over n is 0, and so the limit is equal to 2. So we can easily say that the limit as n goes to infinity of 2n minus 1 over n equals 2. What does that mean? Right? What does this mean? It means that the terms eventually are 2, or really, really close to 2. Essentially, the terms become 2. As you list the terms out, they become 2. And if we look, we can see that pretty easily. So, a of n equals, let's get the set. So let's plug in 1. So if you plug in 1, you get 1 minus 1. So you get 2 minus 1, right? Over 1, so you get 1. In the second term, if you plug in 2, you get 3 over 1, or 2. So you get 3 halves. And if you plug in the next term, you would get 2 times 3 is going to be 6, so you get 5 thirds. Then you're going to get, if you plug in 4, you're going to get 7 fourths, and then 9 fifths, and then 11 sixths, and eventually you're getting really close to 2. That's the limit, okay? Okay, so we can say that the limit is 2, that the sequence converges, and it converges to a limit of 2. Let's look for a more complicated sequence. We're going to be using what's called the squeeze theorem. I think in the book it might say sandwich theorem. In AP, they now want to call it the squeeze theorem. And the idea of the squeeze theorem is that you take this function and you squeeze it between two functions you know. So it used to be called the sandwich theorem because it's like you have two pieces of bread and the stuff in between. You show the stuff in between has to be equal if the bread equals itself. So the idea is you have these upper function, this upper bound, this lower bound function, this unknown function as far as what its limit is as you approach a point. And at that point, if this function that's an upper bound and this function that's a lower bound equal one another, then the function between must also equal one another. And so we start and we look at the cosine of n over n and we say, how do we find the limit of that sequence? And it's not obvious, but one thing we can state is that we know that the cosine of n, of course, in its absolute value is less than or equal to 1 for all n. We know that no matter what, it's never bigger than 1 in its absolute value. So that's all well and good, but we don't have the cosine of n, we have the cosine of n over n. So let's write this as a compound inequality. Negative 1 less than or equal to cosine of n, which is less than or equal to 1. And then let's go ahead and divide everything by n. Now what's nice about this, and you're like, how did you know to divide by n? Well, we're looking for the cosine of n over n, so I wanted the cosine of n over n in the middle. And now I have this. Now we're going to apply what this graph shows. So let's take the limit of each of these separately. So let's do the limit as n goes to infinity of negative 1 over n. And we know that that has to be less than the limit as n goes to infinity of the cosine of n over n. And we know that that has to be less than the limit as n goes to infinity of 1 over n. Well, what is the limit as n goes to infinity of negative 1 over n? That limit, of course, is going to be 0. That has to be less than our unknown limit, which is the limit we're trying to look for, which is less than, and the limit, of course, of as n goes to infinity of 1 over n is also 0. So if this part that we're trying to find has a limit, and we know that this function, or that this sequence is always bounded below by negative 1 over n and above by 1 over n, and both of those have limits of 0, then this sequence also must have a limit equal to 0. And so the limit as n goes to infinity of cosine of n over n is, in fact, 0 by the squeeze theorem or the sandwich theorem. Again, if you're asking, how do we know to do this? What if we have a different type of function here? Couple things. One, often if you have a trig function at the top, you know that you're going to start with this inequality, this rule of thumb of, -1 less than the trig function less than 1. So that's one first step. Secondly, depending on whatever the function is, or whatever the term generator is, the function for the terms, it has to be bounded in some way. It has to be bounded above clearly and below clearly. And the important part is that those two bounds have to have the same limit when you're trying to find the limit. And so when I'm approaching, in this case, infinity, my upper bound and my lower bound have to have the same limit. And so because -1/n and 1/n both have a limit of 0, I know that my sequence also has a limit of 0. It's a little bit of the squeeze theorem. You can look up other videos online if you wanted, but that should be enough to get you started on your homework. Last thing I want to talk about is, why is this different than Chapter 2 limits? And again, I want to point out that, here, for example, is, like 1/n. Okay, if I had 1/n, my function would look like this. Okay. However, if as a function, if f of x equals 1/n. However, if it's not a function, that's not there. If it's just a sequence where a of n equals 1/n, then you have these points. Now, interestingly enough, look what happens if we make a of n -1 to the n minus 1 over n. Now your points go from here and then below instead of above, and then above and below, and above and below, and above and below, and below. And so this is clearly not a function. There's no points in between. But look what happens to these points as they go above and below the axis. Okay? And so the point of this is it's different than a function because there are no values in between these points. There are no values in between these discrete points. Right? These are discrete individual points. Not a continuous function. That's all for day 2 of section 8.1. You go ahead and work on your homework.